Measures of variation. Let's begin with population variance and standard deviation. First, we must understand how population variance and standard deviation are calculated. Also, what do they measure? We also need to learn the correct symbols and notation. This time series graph shows the number of home runs in the major leagues from 1901 to 2013. The mean of this population is 2,346 home runs. But looking at this graph, we see that there's a lot of fluctuation from left to right. The fluctuation occurs in home runs from year to year, and particularly when we get past the 1960 season. And this brings up the question that is asked very often in statistics. How much variation exists within the data? One of the measures that is used to quantify variation in a data set is called variance. The variance is the average of the squared deviations between each data value and the mean. In order to find the variance, we will follow a process. Step 1 is to find out how far does each data value lie from the mean. We will find this by binding the deviations from the mean, which just means we will subtract the mean from each data value. Step 2, we will find the squares of the differences between the data values and the mean. That just means we will square each of the values we found in step 1. Step 3, we will find the average of the squared differences between each data value and the mean. So we will add up all of the values we found in step 2, then divide by the size of the population. The truncated table below contains the data used to form the home run time series graph we saw earlier. Notice that the table contains the year, the number of home runs, and then 2 columns that we will complete together with the deviations from the mean and their squares. Recall that the general rounding rule tells us that we should do no rounding until the final calculation has been made. So we are going to work with as many decimal places of the mean as is practical. To begin, we will subtract the mean from each data value. In the first row for the year 1901, that calculation will be 455 minus the mean. Once that calculation is done, we will square it in the next column. We will continue this process until it is complete for each row in the table. Note that the larger deviation, the larger the squared value will be. The population variance is given the symbol sigma squared. It is the average of the squared deviations from the mean. So we will need to add up all of the values in the last column. This sum would give us quite the large number, as you can see. Substituting into the formula, dividing by 113. The rounding rule for variance is the same as the rounding rule for the mean. We should round to one more decimal place than occurs in the raw data. Since our data are whole numbers, we should round the variance to 1 decimal as well. This brings up the problem of units. The mean for the home runs dataset is 2,346 home runs per season. So the units for the mean are consistent with the units for the individual data values. This is why we can compare the mean to the individual data value when we subtract them in the formula for the variance. But during the process, we squared those deviations and found the mean for the squared deviations. So that means the units for the variance would be the square of the units for the mean. The problem then is that we can't compare our measure of variation to the individual data values. The solution to that problem is known as the standard deviation, and we take the square root of the variance. The result will be a measure that we call, again, the standard deviation. Notice here we are back to the correct units of simply home runs. And notice we are consistent with the units for the mean. The mean are in home runs and the standard deviation are in home runs. The rounding rule for the standard deviation is also to round to one more decimal place than occurs in the raw data. So the standard deviation for this population is 1,575.9 home runs. Variation in a dataset. How does variation in a dataset affect the standard deviation? Let's compare the standard deviation of two similar populations. This time series graph shows the number of home runs hit in both major leagues from the 1901 to 2013 seasons. If we were to describe what the graph tells us, we would probably note that there appears to be an upward trend in the data values. But something else that is worth noting is that there appears to be an increase in variation in the data values, particularly once you get past the 1960 season. So let's separate the data into two populations. We will separate the seasons from 1901 to 1959, and then again the seasons from 1960 to 2013. The two data sets appear to be very different in the number of home runs and the variation from season to season. Much has been made of this increase and its contributing factors since 1901. For example, improvements in equipment and technique are considered as contributing factors. Also, an increase in understanding of the impact of nutrition and training on athletic performance. And finally, then there's the admitted abuse of performance-enhancing drugs, especially in the 1980s, 90s, 2000s, are also believed to be reasons why the number of home runs hit per season is so much greater now. In order to quantify the variation in a dataset, let's recall the process for finding the standard deviation that we learned earlier this video. Recall that the process of calculating standard deviation includes comparing each data value to the mean. Here, the mean of 1,088 for the dataset is plotted against the raw data values in the time series graph for the 1901 to 1959 seasons. The mean here of 3,721 is much higher for the 1960 to 2013 seasons. But notice also that the individual data values tend to stray farther from the mean. The calculation of the standard deviation requires that we first calculate the variance. Recall that in this process, the mean is subtracted from each data value and then squared. These values are then all added together. So the larger these differences between the mean and the individual data values, the larger the variance, and therefore the larger the standard deviation. Due to the greater variation between each data value in the mean, we would expect the standard deviation for the 1960 to 2013 season to be greater than that for the 1901 to 1959 seasons. The standard deviation for the 1901 to 1959 seasons is 621.7. However, the standard deviation for the 1960 to 2013 season is 1,075. So, if we did not have the graphs in front of us, but were instead provided with only the standard deviation for these two similar populations, we would gather from the standard deviations that there is more variation in the number of home runs in the 1960 to 2013 seasons than in the 1901 to 1959 seasons. Sample standard deviation. Let's see how we can calculate a sample standard deviation. Here's a time series chart that shows the adjusted closing stock price for a company we will call Company A for a sample of 18 days. The sample mean closing price is $40.77. And here is a similar graph for another company we will call Company B. The sample mean closing price for this stock over this period is $94.34. There are many factors to consider when choosing an appropriate stock for investment purposes. One of the measures that aids in this decision process is the standard deviation. Recall that the standard deviation is a measure of how spread out the data values are. Both of these stocks appear to have an upward trend in their stock price. But Company B appears to have more variation in its stock price. This variation can influence a decision with regard to risk. In many cases, an older investor would be less likely to be willing to incur high risk in an investment than a younger person. The formula for the sample variance is similar to the formula for the population variance, with the exception of the denominator. Note that the formula calls for us to subtract 1 from the sample size. This is done in order to overcome the tendency to underestimate the population variance when using a sample as a representative dataset. Also, note the use of the letter S as the symbol for the sample standard deviation. Here we have the sample datasets for the two companies. Let's begin with Company A. Note that the formula shows that we will need to subtract the sample mean from each data value. These are called the deviations from the mean. The mean for this data set is $40.77. Once we subtract the mean from each data value, we will then need to square, just as we did in an earlier example for finding the population standard deviation. The difference here is that we are subtracting the sample mean rather than the population mean. The formula calls for us to find the sum of the squares of the deviations from the mean. That sum is 41.9192. Remember that the general rounding rule says that we should do no rounding until the final calculation has been made. So, we will work with as many decimal places as possible and as is appropriate and convenient. Dividing the sum by 1 less than the sample size, in this case 17, will give us the sample variance. The square root of the sample variance gives us the sample standard deviation of 1.570. The rounding rule for the standard deviation is to round to one more decimal place than occurs in the raw data. Now, let's do the process again for Company B. The sample mean is $94.34. We subtract the mean from each data value. Then find all the squares of these deviations from the mean. Then we sum up all of these squares and then divide that sum by, once again, one less than the sample size, again, in this case 17, in order to find the sample variance. The square root of the sample variance will give us the sample standard deviation, in this case of 14.314. Looking at the graphs, we see that the differences in the amount of variation within the data sets is reflected in the sample standard deviations. Now let's go ahead and follow along with your student notes. Let's begin with an example. Here we're going to describe some data using measures of variation such as range, variance, and standard deviation. In this example, we will discuss fading time of outdoor paint. Let's consider the sample of time in months of two brands of outdoor paint and how long it lasts before they start to fade. Let's go ahead and calculate the sample mean time to fade for each brand. The mean for brand A is 35 months before fading, but also the mean for brand B is also 35 months before fading. Now, as you can see, there are various sample data for where the paint started to fade. For example, here in this sample, this person's paint started to fade after only 10 months, whereas this person had 60 months before they noticed fading. And either way, whether it's brand A or brand B, they both have the same mean value for fading. So in that case, we will need more information to truly describe this data. But first, let's talk about range. Now, range is the simplest of the measures of variability to calculate. It's simply the difference between the highest value and the lowest value. So let's go ahead and find the range for brand A, then find the range for brand B. The range for brand A is 60 minus 10, which is 50 months. Whereas the range for brand B, 45 minus 25, is 20 months. So although the means were equal, they both had 35 months for their mean, the ranges are quite different. So for that reason, we should discuss population variance and standard deviation. Statisticians use the standard deviation as a more meaningful statistic than the range to measure variability. Data variation is based on the difference between each data value and the mean. This difference is called a deviation. The deviation of 10 from the mean of the sample of time to fading of brand A is 35 minus 10 equals 25, for example. The sum of deviations of all data in the population about the population mean without rounding will be 0, and that's a problem. To eliminate this problem, what we do instead is we square the deviations, then add the squares, and find the mean of the sum of the squares by the total number of data values, as I'll show you in future examples. This is called the population variance, symbolized by sigma squared. This here is a lowercase Greek symbol, sigma. However, this measure is in the square of the units of the measure of the data. which will be almost of no use to us. To fix that, we take the square root of the variance and call it the population standard deviation, indicated by sigma once again. Now here are the formulas for sigma and sigma squared. Let's start with population standard deviation. The formula for population standard deviation utilizes the summation of the difference between the data value and the mean, quantity squared, divided by the total number of data values inside of a square root, where x indicates each individual value in the population, capital N indicates the population size, and mu, as before, population mean. Population variance simply squares both sides, and we get the following formula. Now normally, these parameters are calculated using technology such as your TI-84. But be sure to round the population standard deviation to at least one more decimal place than the original data, as usual. More often, the sample standard deviation is used because sample data is available more often than data for an entire population. The formula for the sample standard deviation is used to estimate the population standard deviation. However, merely using the sample mean, which is x bar, instead of the population mean mu, and the sample size lowercase n instead of the population size capital N. This would underestimate typically the population standard deviation. Therefore, to fix this, instead we calculate an unbiased estimate of the population variance or population standard deviation by dividing by n minus 1 instead of n. So notice that this formula is very similar to the previous formula of population standard deviation. Again, this is known as sample standard deviation, indicated with lowercase s, where x represents, again, each individual data value in the sample, lowercase n indicates the sample size, and x bar indicates sample mean. Thus, the sample variance is s squared, and simply we square both sides and get the following formula. So why don't we go ahead now and find the sample standard deviation for brand A, and let's recall that the sample mean for brand A is 35 months. Let's go ahead and do this first by hand. Later I will show you with the TI-84. First, what we do is we subtract the mean, x bar, from every data value. This will give us the following results. So 10 minus 35 is negative 25. 60 minus 35 is 25. 50 minus 35 is 15. 30 minus 35 is negative 5. 40 minus 35 is 5. 20 minus 35 is negative 15. Now what we do is we're going to take each one of these values here and square them to get the next row. Squaring each of these values gives us the following. Now finally what we do is we take all of these values in this row and add them up, giving us 1750. We simply get the square root of the 1750 that you see there, all divided by n minus 1. Well, as you can see, there are 6 sample data shown. So I shall put 6 minus 1 in the bottom. Results in 1750 over 5. Plugging this into my calculator, and we round to one more decimal place than the data values. As you can see, our data values are whole numbers, so I will need to round to the nearest tenths place. That will give me 18.7. Now let's take a look at a shortcut formula that does not use the mean of the sample. This formula will also give you the same result if you are not given the mean or if you do not want to calculate the mean of the data values you are given in your sample. Let's go ahead and find the sample standard deviation for brand B, this time using the TI-84. First, we will enter the 6 data values into one of your lists by first pushing Stat, then Edit. Next, enter your values, then push Stat again. Then go to Calc, enter the first option, 1 var stats. From this, you will find the standard deviation of brand B. And the sample standard deviation for brand B will be 7.1, as indicated from this here. The calculator uses the symbol S sub x for sample standard deviation. Sigma sub x will actually be your population standard deviation. But here, the population wasn't given, just a sample. What does this indicate about the variation of the two brands? Although both brands have the same mean, brand B's time before fading is more consistent than brand A, meaning that brand A's sample standard deviation was 18.7. The sample standard deviation for brand B was 7.1. This means there's a lot more variability in brand A than brand B, making brand B a more consistent brand. Here are some uses of the standard deviation. The standard deviation provides a measure of spread or variation of the data. If the standard deviation is large, like brand A, then the data are more dispersed, more sporadic. It is used to compare the variability of 2 or more data sets. As you saw from the previous example, brand B had a smaller standard deviation, which made it more of a consistent brand. Less variability, less sporadic. 2. The standard deviation is used to determine consistency of a variable's values, as mentioned before. 3. The standard deviation is used to find the number of data values that fall in a specific interval in a distribution. 4. The standard deviation is used in inferential statistics. Coefficient of variance. The coefficient of variance is a statistic that allows comparison of standard deviations of datasets having different units, such as a variable measured in inches and another variable measured in centimeters. The formula for the sample coefficient of variance, C bar, is expressed as a percentage. As you can see, it's the sample standard deviation divided by the sample mean times 100. Population C bar would be the population standard deviation divided by the population mean, again multiplied by 100 to make it a percent. Use this formula when asked to find the coefficient of variance. As a side note, a rough estimate of the standard deviation can be found as follows. Simply take the range and divide by 4, and you will have a rough estimate of the standard deviation. Chebyshev's theorem. The standard deviation of a variable measures spread or dispersion of the variable. The larger the standard deviation, the greater the dispersion. The smaller the standard deviation, the less the data values are dispersed, and the data values are more consistent. Chebyshev's theorem finds the proportion of spread in terms of standard deviation. The theorem applies to any distribution regardless of shape. Here's the formula for Chebyshev's theorem. The proportion of values from a dataset that fall within k standard deviations of the mean will be at least 1 minus 1 over k squared, where k is greater than 1 and not necessarily an integer. Let's try an example. Americans spend on average 2.85 hours per day online. If the standard deviation is 32 minutes, find the range in which at least 75%, that is when k equals 2 standard deviations, and also 88.89%, that is when k is 3 standard deviations from the data, will lie. To solve part A, first, let's change the average to the same units as the standard deviation. 2.85 hours equals to 171 minutes. Simply multiply 2.85 by 60 minutes. Having said that, we can now continue. For k equals 2, we simply follow Chebyshev's theorem. That is 1 minus 1 over 2 squared, simply replacing k with 2 in the formula, which clearly gives me 1 minus 1/4. 1 minus 1/4 is 3/4, which is 0.75, rather 75% as indicated. So here, as we can see, when k equals 2 is plugged into Chebyshev's formula, it does give us the 75% as desired. What we shall do next is we shall add 2 standard deviations to the mean and also subtract 2 standard deviations from the mean as follows. Let's first add. By adding 2 standard deviations to the mean, we see that we get 171 being the mean plus 2 times the standard deviation of 32 minutes, which gives us 171 plus 64, 235 minutes, rather 3.92 hours. Now we must subtract 2 standard deviations from the mean. That will give us 171 minus 2 times 32. Again, 2 being how many standard deviations, 32 being the standard deviation itself. 171 minus 64 gives us 107, rather 1.78 hours. Thus, by Chebyshev's theorem, at least 75% of the data is between 1.78 and 3.92. For part B with 88.89%, that means we need 3 standard deviations. It's a similar process. Again, let's note how k equals 3 lines up with Chebyshev's. For k equals 3, we see that 1 minus 1 over 3 squared gives us 1 minus 1/9, which is 8/9, and as a percentage, that will be, in fact, 88.89%. So once again, we're going to take the mean and add 3 standard deviations to it. So this time 3 times 32, which is 96, which gives us 4.45 hours. But also, let's not forget to subtract 3 standard deviations, this time giving us 75, or rather 1.25 hours. Thus, by Chebyshev's theorem, at least 88.89% of the data is between 1.25 and 4.45. Let's take a look at another example using Chebyshev's. The average number of trials it took a sample of mice to learn to traverse a maze was 12. The standard deviation was 3. Use Chebyshev's theorem to find the minimum percentage of data values that fall between 4 and 20 trials. Before we can actually do this, we must first ask ourselves the question, how many standard deviations from the mean is 4? In other words, we take the mean and we subtract the standard deviation times how many standard deviations of k and set it equal to 4. Here we get k equals 8 over 3, and notice it's not an integer, but this is how many times we'll need to multiply by the standard deviation to get to 4. Also, how many standard deviations from the mean is 20? Again, in other words, 12 plus 3k this time equals 20. Once again, solving for k, we get 8 over 3. And now we can go ahead and use Chebyshev's. And the reason why we can use Chebyshev's is because 4 and 20 are the same number from the standard deviation as the mean. So for k equaling to 8/3, using Chebyshev's, the percentages, and after multiplying by 100%, we will get 86% in this case. The empirical or normal rule. While Chebyshev's theorem applies to any distribution, regardless of shape, the empirical rule applies only to bell-shaped data. By the empirical rule, for a distribution that is bell-shaped, approximately 68% of the data values will fall within 1 standard deviation of the mean. Approximately 95% of the data values will fall within 2 standard deviations of the mean. Approximately 99.7% of the data values will fall within 3 standard deviations of the mean. To illustrate, all these vertical bars represent data values. And as you can see, we have our mean here in the middle. If I move 1 standard deviation to the right and 1 standard deviation to the left, we fall within 68% of all data value reported. Going out another standard deviation, we can see here we fall within 95%. Finally, 3 standard deviations falls within 99.7%. See an example? The average math and reading SAT scores. The average math and reading SAT score in 2014 was 1010. Suppose the distribution of scores is approximately bell-shaped and the standard deviation is approximately 86. Let's answer the following questions. Within what boundaries would you expect 68% of the scores? Also, let's answer, what percentage of scores would you expect to be above 1182? Let's begin with part A. Within what boundaries would you expect 68% of the scores? Well, according to the empirical rule, I would expect that 68% of the data values will fall within one standard deviation of the mean. Therefore, the upper boundary will be mu plus sigma, which would be 1010 plus just one standard deviation, so 1 times 86, giving us 1096. And the lower boundary will be similar, but with subtraction. 1010 minus 86, in this case, equals 924. Thus, I expect 68% of the data values to be between 924 and 1096. Now, what percentage of scores will be above 1182? First, let's find the number of standard deviations that the value is from the mean. We will use the following formula. We will simply take 1182 and set it equal to the mean plus the number of standard deviations from the mean times the standard deviation. In other words, 1182 equaling to 1010 plus k times 86. Subtracting both sides by 1010 will give us 172 equaling to k times 86. Dividing both sides by 86, we see that we get 2 standard deviations from the mean. Therefore, to finish up part B, by the empirical rule, we expect that 95% of the data will fall within 2 standard deviations of the mean. So, the remaining 5% is evenly split between the amount of data values above and below the mean. Splitting that in half, that means that 2.5 of the data is expected to be above 1182. In other words, 2.5% of the population of students taking the SAT will have a score of higher than 1182.